Okay, in this activity, we are going to compare the means of two separate populations. Listed are student course evaluation scores for courses taught by female and male professors. We're going to use the 0.05 significance level to test the claim that the two samples are from populations with the same mean. In other words, we want to know, we're assuming that the average course evaluation score for courses taught by females is the same as it is for males. So is there a difference in the evaluation courses taught by male versus male professors? Okay, I've done some of the background work here. I did the summary statistics, put all this information into StatCrunch and came up with a mean score for the female professors was 3.8 and so forth, and a standard deviation of 0.56 and so forth. The mean for the male professors was 3.99, so forth, and standard deviation of 0.395 and so forth. Okay, the trick here is understanding how you're going to set up your null hypothesis and your alternative hypothesis, as well as how are you going to identify your degrees of freedom. So this part probably isn't too strange. After we do our next section, the difference between the two might kind of throw us. But here we're looking, our null hypothesis is that the average scores are equal to each other. You could also state it as the difference between the two scores is equal to 0. That's the claim. Our alternative is that they are not the same, or that the difference is not equal to 0. So you could write it either of two ways here. Looking at our confidence level is 95%, our alpha is 0.05. I need you to insert another 0 in there. I went through this too quickly, but I got that from this second line right here. Okay, our sample size that we're going to use is 12, and our degrees of freedom is 11, simply because this is the smaller of the two populations, but also these are different populations. So we are going to assume that we don't know that the sigmas are equal to each other. Basically, we have to use the smaller of the two when they are not pulled from the same population. We can't pool them if they're from different populations. So degrees of freedom is 11. Our critical value is going to be plus or minus 2.201. Also, keep in mind this two-tailed is because it's an inequality here. That also tells us we're going to have an upper and a lower limit. This critical value of 2.201 I got from the t-table. Now again, our degrees of freedom was 11 and our significance level was 5 for a two-tailed test. So I'm going to go across here and find the 0.05 for a two-tailed test and go down to the degrees of freedom 11 in the very middle. T-score is the one that we're looking at here, 2.201. So that's how I got that. Going down and plugging into this lovely formula, you have to keep in mind which is your first population, which is your second population. I've identified the female as the first population, minus the difference of the two mu's, and our population claim is that they're equal to each other, so that difference should be 0. So that's where that 0 is coming from when I plug that in. Other than that, I'm plugging in the means for both the female and the male, finding that difference. Our standard deviation squared for the females here, standard deviation squared for the males here, and I forgot to put a square on there, so I need you to definitely put a square on that, 0.39. The sample size for females was 12, sample size for males was 15. So that's when we plug all of that in. We came up with a test statistic, t-test statistic, of negative 0.657. So that's on the lower half of our curve, but not nearly as low as our critical value. So we know, just looking at those scores, comparing those t-scores there, that we're probably not going to be rejecting anything. When I draw the picture here, I actually should have drawn in the upper limit here, critical value of positive 2.201. I was just more concerned about everything going on in the lower end of our curve. But we can see that it doesn't fall in the rejection zone. The p-value, to get the exact p-value, but I have to go to StatCrunch, and so I might as well do that right now. And I am going to try to, okay, we're going into stats, t-stats, we're going over to two samples this time with summary. Okay, so I'm going to need to put in my sample mean of 3.866667. The more decimal places, the more accurate we are. We have small sample sizes, so that's going to be important. Our standard deviation is 0.563, 001. Our sample size for the females was 12. Looking at the sample mean for males, we have 3.993333. Our standard deviation for males was 0.39545. Our sample size for that was 15. Okay, and at that point I can pretty much go ahead and just click compute. I end up getting a little bit different test statistic, t-stat, than what I had here, and probably that has a lot to do with that I didn't have the full digits in here. I don't believe I had the full digits in here either. So again, those place values can make a difference. But my p-value is right at 50% almost. I mean, the p-value is high, so that whole idea that the null will fly is going to support that as well. But being I'm in here, I'm going to go ahead and do the confidence interval. So I'm going to click edit, and I'm going to come down here and do confidence interval. We're going to leave that at 0.95, so we're good to go. And we end up getting a confidence interval where you have negative 0.528 to a positive 0.274. So 0 is in that confidence interval. So again, we're probably not going to be doing any rejecting here. So when I plug all of this in here, and came out with a little bit different p-score, again, because I probably didn't have my full digits here. But we can see that 0 is in our confidence interval. So it could be that the difference really is 0. So there's no way. All three methods support that we should not reject. There's no way we should reject the null hypothesis here. So we are going to fail to reject the null hypothesis. There is not sufficient evidence to support the claim that there is a difference in the course evaluation scores for courses taught by males versus females. I probably could have stated that a little more clearly there. Okay, in this video, I just really quickly want to revisit this problem where we were looking at the course evaluation scores for female and male professors. I just want to show you very quickly how you could work with the information if you have the raw data. I had given both the raw data as well as the summary statistics when we originally did the problem, but you will have problems in my math lab that is going to give you raw data. And I just want to show you very quickly how you can handle that. I'm going to go into StatCrunch. What's nice about StatCrunch now is it spills the data automatically, or I'm sorry, my math lab will spill the data automatically into StatCrunch, so you very easily have it ready to go. You don't have to do any of that entering. But you would go to Stats, T-Stats, and we're going to do toSample, but this time we're going to say with data. Okay, your values for your first sample are in the first column, and the values for your second sample are in bar 2, the second column. You don't need to identify where. We are not ever going to use the pooled variances, so don't worry about that. Hypothesis test, in this case, we were looking at these evaluation scores having equal means, so we don't need to change anything there. What I do want to show you is you can go down here and click on summary statistics, and it will give us that as well. So whether we click on that or not, that's the way to go. The hypothesis testing is done very similarly, all behind the scenes for you. So it gives you the t-stat and the p-value, but it also gave you this sample statistics chart if you need that for any of your questions. You can always go back and do the options again and do the confidence interval. I believe we need to leave that as is, and we can get the confidence interval as well. So the StatCrunch can really help you out and make life easier.